Hello everyone. Today we will complete our view of the application layer, and then we'll talk about a few deviations from the architecture, the module I call IP2. So for now, let's continue our exploration of the application layer. DNS is typically put in the application layer, although we could view it as a service to the internet. We all know how to use DNS. Perhaps what we don't know exactly is how it works. What happens when I use the DNS? The DNS is a set of DNS servers that contain the information that maps names to addresses, and it's a loosely synchronized distributed database. It's the collection of all the servers that makes the information available. For example, at EPFL, there is a DNS server that contains one or several copies for reliability of a DNS server that contains all the information about the addresses and the names given by EPFL, so in the domain epfl.ch. And that is the root of all information about epfl.ch in the world. The rest of the world has only cached values of this. We'll see how this works. Lisa here clicks on a web page that contains a reference to this machine, www.zurich.ibm.com. Lisa's software associated with a web browser is probably a function called a DNS resolver that will ask a DNS question, message number 1, to the DNS server. Remember that every configuration of an IP system calls for the address of a DNS server, one or several. So you try one of them, and we see that the computer here asks the question, what is the address that corresponds to that? In DNS terminology, capital A means IP address. Quadruple A, IPv4 address. Quadruple A means IPv6 address. So here, the machine is asking for an IPv4 address that corresponds to that. And it asks the question to the DNS server of EPFL. The DNS server of EPFL in this case doesn't know, because it's not the IBM DNS server. But it knows that IBM.com is under .com. So all DNS servers must know at least a few information that's used for bootstrapping, and the information they know is that of the addresses of what are called the root servers. There are less than 20 root servers in the world that correspond to the domain, the top-level domains, like .com is one of them. So the DNS server of EPFL will send to one of the root servers the query, which is the same. As we can see, it's the same query here. Then this doesn't know exactly, but this one knows the IP address of a DNS server that has authority about the IBM.com. Why? Well, because .com is a parent domain of IBM.com. So when you create a domain like epfl.ch, you have to have authorization of the parent domain. In the case of EPFL, it's the .ch domain. And you need to give to the top level, to the domain that's above you, you need to give the addresses of at least one and hopefully more than one DNS servers for your domain. So .com knows the IP address of a few DNS servers of IBM.com. And this is what is the information that's returned to the DNS server of EPFL, which is acting as a proxy for Lisa. Then here, we still don't know the answer, but we know more. We know whom we should ask. In that case, we should ask one of the machines that is returned here. So the question is asked by the DNS server of EPFL to in that machine at IBM that returns an answer, and the answer contains what we want, which is the IP address of the machine, 193.561.131, as well as a time to live in seconds. So here, 2 hours. We'll see what the use of the time to live is. Here we see that the DNS server of EPFL has acted on behalf of Lisa. It's what we call a recursive server. So this server offers a rich service. You ask one question, that's what Lisa did, and then the server does many calls to the DNS to find the answer. very much like a recursive function. You call it once, and it may call itself several times, but you don't see that in the code that calls the function. So here it's called a recursive use of the DNS. Recursive use of the DNS is in principle done only by DNS servers that serve their customers. So the EPFL DNS server will do that for you, but the IBM or the root servers will not do it for the rest of the world. They will simply immediately give the information they have. They will not keep the request here. There's a price to pay for being recursive. During all the time, from 1 to 6, the query is stored here in the DNS server of EPFL. So it's keeping state relative to this query. So it is providing a rich service, a bit like a web server would do. We can directly, with programs like NSLOOKUP or DIG, you can directly see in your machines, in your command line, in Windows, in Unix, you can do the same. Here, for example, I'm asking an A record for this machine, and you can see exactly the answers, which are simply copies of what is available in the DNS server. Here, I'm asking the same question, but with quadruple A, and this means I will return the IPv6 address, if it exists, of this machine here. Here we have a machine that has both. If I want to have IPv4 and IPv6 address, I need to ask for both explicitly. We have seen that there's a time to live in the request, and the reason for that is, of course, like we have seen in many other opportunities, in many other settings, the results that are returned from when a DNS server like this one has learned about the IP address of a machine at IBM, it will keep it in a cache. How long should the cache entry be kept? Well, that's one of the difficult issues with caches. That's one of the problems with caches in general. Here in DNS, this is controlled by the originator of the DNS record. In that case, the IBM DNS server puts a value, and then you simply copy the value that you receive here. So here, this means the EPFL server will keep during 2 hours this value. Which means that if a bit later someone else at EPFL on another machine, but being served by the same DNS local server, asks the same question, what's the IP address in order to go to this web server of EPFL, then it will receive the cached value. That's efficient. We don't need to ask the same question many, many times. Most people go to YouTube, to IBM, to Microsoft, to etc. So most queries can be mutualized. We can work on them only once. But it has a drawback. What's the drawback? Yes? We can do cache poisoning. Well, for that, you need to be able to speak to the DNS server of EPFL. Right? Yes, you can do that. But with or without you can do that for every value of the time to live. Right? The time to live, depending on its value, will have some behavior or not. What if the IP address of the IBM server has changed? Why do IP addresses change? Well, it can happen that the server is down, for example. You're installing a new server, you give it a new IP address, that may happen. Then if the IP address of the server has changed, during 2 hours, you will still get the old address. So if it's really due to a crash and a replacement, during 2 hours, the service will not be accessible. So if you want to have addresses that are very dynamic, you should not give large values of the cache, of the time to live here. When we do traceroute, which we did at the beginning of the course, we see things like this. So here, I'm doing a traceroute to some address here, and I see a list of intermediate systems. We know how it works. It is by increasing TTL. So we send a test message, which is either ICMP or UDP, depending on the version of traceroute. And with increasing TTL, and the error messages sent by the intermediate systems give us who they are. But we see the IP addresses and the names, right? Of course, the names are not in the ICMP messages. They are the result of what is called a reverse query. It is the traceroute software that gets the IP address and obtains the corresponding name. So it's the printing software that does it. It's not the mechanics of traceroute itself. How do you think that you could do such a thing? If you have a program whose job, like traceroute, is to pretty print names instead of IP addresses, how would you do it? So the majority thinks that traceroute asks intermediate routers, what is your DNS name? I don't think you want to do that with routers. Right? Routers are real-time machines. Their job is to forward packets as fast as they can. If you start asking them such questions, probably they wouldn't bother answering. They will just discard the questions. You can be happy already if a router sends an ICMP message saying TTL exhausted. That's already a large amount of work for a router. Not all routers do that. If you ask them, what's your name, which requires going to higher layers of the router, it won't do it. So that's not how it works. The normal thing, if the DNS would be a true database, this is what we would do. A database is like big arrays of entries and fields, and you can access a database by whatever entry you want. You can ask, if you put DNS content into a database, you could do queries like this into the database. Ask, what is the name that corresponds to the IP address? But what's the problem with databases? Who has done a software project with MySQL or other things? Okay. So what was the problem with the database? Or the benefits? It's very convenient for the programmer. Just put all the information into a big thing and you don't bother about how it is stored and all that stuff. If you have a simple program and a single machine, it's fine. If you start having very large things, I mean, the scaling of databases requires considerable sophistication and a lot of work. Otherwise, it is slow. So that's the slow part of many websites. You go somewhere, you ask for a database, then the website takes some time to answer, so it is slow. There is worse than that. What's the major problem for databases? It is that of consistency. A database must be replicated. Otherwise, if you lose one computer, you've lost everything. So you must replicate it. Also for performance, if you have a single computer that runs the database, you will not scale to a large amount of traffic. So you will need to replicate your database. If you replicate the same thing in multiple machines, here starts the monster of distributed system and the impossibility of consistency. We know in the real world, if the network can lose messages or delay them arbitrarily, it is impossible to guarantee that replicated copies will be exactly consistent 100% of the time. This is why distributed systems always have strange behavior. Once in a while you need to reboot, restart, whatever. It's mathematically impossible. That's one of the results of distributed systems theory, and those of you who took this course know about that. In DNS, we give up consistency. We put caches everywhere, and the data is correct at one point, or bad luck, you have the data that was the correct one 5 minutes ago. If it has changed somewhere, we don't guarantee that the changes are consistent everywhere. We do that all the time in networking. OSPF does the same. When a route changes somewhere in OSPF or BGP, we don't guarantee that the routes are synchronized everywhere, and before we send a packet, all routers in the world must have been aware of the change. We don't do that. We accept the fact that there may be inconsistencies. Inconsistencies will result in temporary loss of service. A packet may be caught in a loop. We have seen that in OSPF, when it repairs packet loss, link losses, it may have temporary periods of times during which the routing has a loop, for example, and then the packets that are caught in the loop will die because of TTL exhaustion. So we accept that things are not perfect in the internet, and we therefore do not enforce consistency. That's what we do with DNS. DNS servers are not exactly consistent, and we don't do a reverse lookup. Instead, what we do is something very simple-minded. We ask the people who do put in IP names corresponding to IP address to do the reverse lookup by writing records in one direction and records in the other direction, which for database people is a horror. You would never do that because you have the information already. But you do it because you don't want to have all the other dark side of databases. So those records are called PTR records. And for example, a well-managed DNS server, like the one of EPFL, will put all the names that correspond to allocated IP addresses, and vice versa, will put a list of records that are sorted by IP addresses with the syntax of a name. So the syntax of a name is that one. This is how you write an IPv4 address when you write it in the syntax of DNS. So you will put all those records statically. And then when DNS lookup goes for, when traceroute does a reverse lookup, it simply asks what is the pointer record that corresponds to that address here. We see that here, for example, I can ask what is the name of this, and I will find as a response, I will find this name here, and I can check by asking what is the IP address that corresponds to this name. I will find the same. But if I do the same for other more funny names, like if the name Freedom to the Galaxy, that was at some point put by some DNS server just as a joke. So if I ask what is the IP address that corresponds, what is the name that corresponds to the IP address, I will have this name. And nobody so far, I think, has bought the DNS name Galaxy. So this is an invalid name, but it's put in the DNS. And you see that if you do the reverse lookup, it doesn't work. Right? So we find here a feature of DNS. It's a loose system. There is no guarantee that everything works as expected. The guarantee depends on who is originating the names. The authority about this is delivered at the top by something very controversial. Right now there is a company called Public Technical Identifiers, formerly ICANN. The controversy comes from the fact that ICANN was an American company that is in some sense controlling all the DNS, and the law that applies to that company is American law, Californian law. This has been replaced by an international consortium with countries of all continents that run the top-level authority. So the top-level DNS servers are themselves run by commercial companies. And then those top-level authority allocates the top-level domains. So the two-letter domains are allocated to countries. .ch is us here in Switzerland. So in Switzerland, the Swiss government must appoint one agency to be what is called the registry. The registry is the entity that receives delegation from the government to set up the rules for how the names are allocated. Now, name has to do with technology, with TCP-IP, but also with law. Because if I am called Dupont and I want to take the name Dupont.ch, and if the company, the chemistry company Dupont, also wants to claim that name, I mean, who will resolve, am I allowed to do it or not? So this is why all of those allocations have to do with politics and the government. Register is the commercial companies to whom you go if you want to do your own DNS name. They sell to you the name. So they don't sell much. They just guarantee that this name is not taken and that you continue to pay every year to have your record written there. And then you need, of course, once you have a name, you need to put it in a DNS server, which is yet another business. EPFL runs its own DNS server. If you want to have your own name, you will need to pay or find a free DNS server somewhere to put the root information of your domain into this server. There are some attempts to get rid of that. If you're interested, you can look at how the .bit domain works. It's used for a completely peer-to-peer system where there is none of that authority and registries and all that stuff using blockchain technology for completely peer-to-peer. Not very popular yet, but who knows?
Excuse me?
Yes?
A question about the root domains. It seems like every DNS query which wasn't found in cache goes to root domain first.
No, it goes to It goes to the root domain if you have no other information. For example, if you're looking for a question about IBM, and you have the information that is not yet old of what is the DNS IP address of the DNS server of IBM, then you will go directly to that server. And so on. If there are several levels in the hierarchy, you will go always the next level for which you have the information. If you have no information about a part of the tree, you go to the root.
But still, it seems like this root service should be one of the most loaded resources in the whole internet.
Correct.
And as a result, it should cost tons of money to support them. And I'm just interested who pays for that.
It's a good question. I don't know who pays for them. They are run by multiple companies. It's a good question. I don't know the answer. You can look it up on
So it's kind of charity because they don't make any money?
I'm not sure you run a computer for charity, but they must receive money from somewhere. Yeah. I don't know who pays. There's several options possible. Large companies could pay, or governments. So the DNS was originally invented because people thought we prefer to write names than addresses. This is not really a very good argument anymore today because we don't write names either most of the time. When we want to go somewhere, what do? Right? If you want to know how should I fill in my tax form, where do you go? You do a search, right? You go to a search engine, and therefore the interest for DNS as a human-readable name has largely decreased. But it finds other interests, and one of them, which is very, very commonly used, is to do what is called load balancing. Here is an example. Assume you have a company, Softcom, that wants to respond to one address, www.softcom.com, but you want to split your web server on many, many different machines. One way to do it, particularly if the machines are in different sites, in different countries and different time zones, one way that's very often done is you allocate the same name to a large number of different machines, and you put into the DNS all those entries here. So and you associate that with a very short time to live, order of less than a minute. And then you buy a DNS server on your side that has some load balancing feature. Load balancing feature means whenever a request comes to your server for one of those names, it will randomly or through some round-robin policy pick one of those. So that you will distribute to the world a mixture of all those addresses. And if the TTL, the time to live of the DNS record, is very short, then this will provide exactly the kind of flexibility you want, which is to allocate the work to those different machines here. So this is typically what Google does, for example. When you go to google.ch, you go to one of those machines. That changes all the time. We've seen before that we can attack the DNS, we can poison the cache, we can poison the replies, you can pretend to be IBM.com, and for some parts of the DNS it is true today, and it's a well-known attack against services. Not surprisingly, there is a solution which is very similar to the problem we saw with BGP, except here the solution is more realistic to implement. The solution is to encrypt and authenticate the DNS responses. So if I go to the IBM.com server, it's like if I go to an IBM server with HTTPS. There are mechanisms called certificates that use asymmetric cryptography to make sure, with reasonable assurance, that the machine I'm talking to is really in the IBM.com domain, is really a DNS server of IBM and not somebody that pretends to be so. So this is done there are two approaches to do that. One of them is to use DNSSEC. DNSSEC is a set of rules for how to use cryptography to sign the records. In BGP, we have the problem that the same solution applies, but the problem with BGP, we need to do it for every BGP update. And if there are many, many updates that we are propagating, we need to sign them all the time here. Here it's the same for DNS, but for DNS is less time critical than BGP. Right? If there's a change somewhere in a router, in the interconnection, you need to update a massive number of routes. With DNS, it's considered to be a bit less time critical. So this is deployed. Some countries deploy it systematically. Some companies deploy it systematically. Some alternatives are also have been proposed. Is, for example, to access the DNS not using the DNS protocol natively, which uses UDP and its own mechanism without relying on TCP, for example, but to use a TLS, which is TCP plus security, authentication and encryption, or QUIC, which does the same thing without the drawbacks of head-of-line blocking of TCP. So there are currently versions of DNS clients and resolvers that use DNS over TLS or QUIC, and then you get the authentication from TLS. Very similar to what you do when you go to your bank for e-banking. You go via TLS and HTTPS, and then you have a certificate that's verified by a web browser. Here it's the DNS resolver that will verify the certificate. Apple was very famous for living without DNS. At the very beginning of Apple networking, there was nothing, the addresses were names. So Apple, at the beginning, started very radically. There was no address. MAC addresses coming from the hardware. And then the network layer addresses were name, which is very smart because then you don't need to have addresses. So if you would install an AppleTalk printer, you give it a name, my printer, room A32, and that was the address in some sense that was written in the AppleTalk packet for this machine here. One benefit of that was also when you were searching for something, for example, a printer or a network-attached storage system, you can send a broadcast query asking everybody, are you a printer? And everybody who is a printer would respond to you with their name, which they know because it is their address, so you don't need a server. Apple did that for a number of years, and it was the success of the Macintosh was in part due to things like this that made it everything plug and play. You didn't, like you do today with TCP-IP, to have a DHCP server with blocks of addresses and this and that. You didn't need all that. It would be plug and play. The only thing you need is to give names to machines. But of course, AppleTalk did not survive, at least as a network layer protocol. It was superseded by TCP-IP. So Apple went through the difficult job of migrating everything into TCP-IP, but they kept the goodies of AppleTalk, and one of them is called this serverless DNS, which is called Bonjour, which works only within one local area network, so one subnet, where if you are a printer that is configured with a name, for example, anybody who wants to know who is this printer, for example, can simply send a query to the multicast address. So instead of having a DNS server that would have a list of all the names and their IP addresses, you simply broadcast. It works, of course, since you broadcast inside a single local area network. In principle, we don't want to do broadcasts that go beyond a local area network. So that's an alternative that does not scale. When you search for a name, you can have a database or something like a database, that's the DNS, or you can do broadcast, which we have seen in other contexts. We've seen another way of resolving one thing to another, which is MAC address resolution. I know the IP address, I want to know what's the MAC address. In that case, we use ARP, which typically is like bonjour. We ask everybody, who has this IP address here? We can do the same for names. Quick question, assume we change the IPv4 address of this server. How long will it take for the world to become aware of that? And the answer was written here, right? So the TTL here gives exactly how long the entry will be valid. Static things like EPFL tend to have very long times in order to reduce traffic. The DNS server of EPFL will be exposed to a much smaller set of external queries because the things stay the same for entire days. Other systems like Google or content network providers will tend to do the opposite, to have very small value. And I invite you to test it on your machine. That's all we'll see for DNS. Any questions? Then if not, we move to something called the application layer gateway. When we configure a machine, we see that sometimes we're asked what is the default gateway. Gateway is not the same as this gateway. Default gateway was the name in the 1970s for an intermediate system, which at that time was typically a router for the internet or an application level intermediate system for other networks like IBM SNA. Today, when we say gateway, we typically mean an application layer gateway. So what is an application layer gateway? Well, it is something that's an intermediate system for the application layer itself. One example of gateway is a web proxy. A web proxy is a machine that needs to be configured in your web client, where instead of going to a remote server, you go to an intermediate system. So you send your query to get a file, for example, to that system that will terminate the TCP connection, analyze what you're doing, see whether it likes it. For example, a gateway might be filtering things. There are sites you're allowed to visit, sites you're not allowed to visit. And then, or things, queries you're allowed to send, others you're not allowed to send. So we'll analyze and filter and then send it again here. So it might be for filtering. It might be used also for performance. Could you see an advantage in terms of performance for doing such a thing? Yes? We could cache. So one motivation for web proxies like this one is to say, well, the bandwidth between us and, for example, California is very expensive, and if EPFL students use it a lot, EPFL will need to pay a lot to switch, so we want to reduce that because, after all, you're all watching the same thing, so the very popular YouTube videos, you can store them here. That was an initial motivation, which is now a bit decreasing because much content is in fact very dynamic, so it's very hard to cache. But that is a motivation. Another motivation is also performance. If, for example, this is a wireless link where you may have, because you're mobile, like most of the time when we're accessing the internet at EPFL, we do it over a mobile network or Wi-Fi. And we know that if there are losses in a TCP transfer, the performance will be badly hit. Now, if you're accessing data from the other side of the world, if there is a loss here, as we know, the window, in the best case, the target window will be decreased by 2. Sometimes we can even go into slow start. So there will be a large performance hit, and the larger the round trip time, the worse it will be. So one idea very often is to break the lossy link into short RTT things. So if there is a loss here, you will repair it very fast. And the throughput here is also very large, so the bottleneck is not here. But when going from the proxy to the internet, you go over a wired network where hopefully you don't have any of those spurious losses. So performance enhancing proxies are due to, in some sense, the fact that we were not able to engineer congestion control in a way that does not have these problems of RTT unfairness and problems when the losses are not due to congestion. So that is the example that was suggested to use a proxy to reduce traffic. Question?
Is this done often, or is it not so often?
So is it often done to have a proxy like this one to improve performance? It's very often done in cellular network, yes. That will try as much as possible to hide, to do things for you here, as much as they can. Very often they cannot. In particular, if the data is encrypted end-to-end, it's very hard to play with the data other than to do TCP connection piping. But in general, the philosophy of the internet, if you remember from the very first day of this course, we saw that the internet was built on the principle of packet switching, which defeats the purpose of this. If we do packet switching, we can transfer information from A to B end to end. So this has been formalized in the internet architecture and design in the form of what is called the end-to-end principle. The end-to-end principle of the internet says that we should not have application layer gateways, or in fact, we should not have any intermediate systems other than at the network layer or the MAC layer. All the layers above should not have such intermediate systems, because the principle of the internet is we deliver all data into small packets that are all the same, and all packets can be transported end-to-end. This is what made the success of the internet. During more than 10 years, the internet was a very boring and hard-to-use network. When HTTP and HTML were invented, it was very easy to invent it because there were no intermediate system layers. It required no intermediate systems to be deployed here. Unlike other systems like video text that was requiring the store and forward systems. However, it's not always possible. Like every principle in life, you should adhere to it when it makes your life simpler. When it does not, you should think twice. What would give an application of the end-to-end principle to email, for example? Well, here I'm showing two intermediate systems, right? If I send a mail to one of you, you read it on your smartphone, I send it from my smartphone, so the end-to-end principle say I should send it from my smartphone to your smartphone. Right? This is what the end-to-end principle says. Why don't we do it that way? Yes?
It's like with actual mail, we don't send the letter to the person directly, to his mailbox, so that when you go home, he can retrieve his letters. So that's the way we send.
Exactly. So we send it to an intermediate system so that all the information is kept there. So the interest that we want is to send it here and not there because of mobility. We want to be able to access the data from anywhere and from a mobile system that is perhaps connected, perhaps not connected. So all messaging systems, SMS, WhatsApp, all that stuff, they have servers in between. You send to a server, the server sends to the mobile, so they are application layer intermediate systems. Right? That's one of the reasons. Other reasons are authentication and security. If you go to a private company like this one there, you get internet access, everything looks nice, but if you go to some sites, you get a web page like this one, right? It displays another web page because of whatever reason, the company policy forbids going to other servers. So we have a web proxy here that's in the middle. Whenever you're in Romande Energie and you go to a website anywhere, you first go to a web proxy that will verify what you're doing here. Another example of intermediate systems that is extremely frequent in data centers is load balancers. They're called server-side load balancers because they sit in the data center, not on your machine here or on a cache at the local system here. So assume, for example, you're going to one of the big companies, CFF, Google, whatever. They receive zillions of requests every day, and they have not one computer, but huge rooms full of computers, so thousands of computers are in parallel processing all the requests. And in order to balance the job between those different computers, you go first through an intermediate system. So if I connect to a website, in fact, I will first go to a first gate here that will simply analyze my requests and forward it to one of the data centers that will of the data center number crunchers that will do the job for me here. How would you do that? How would you achieve this? If you're in charge of a data center for your pet project and it becomes so successful that you have to do a load balancer, how would you, and assume, for example, if I could have a single load balancer, but if I have a single load balancer, I would have an obvious problem of what would be the problem if we have a single load balancer in our data center? Reliability, yeah. Or it could become the bottleneck, but the idea of the load balancer, it simply forwards the data to one of the machines. So it's looking at the data, put it in a format that is perhaps simpler or simply repeats it, but has some logic here to get some statistics from those different machines to know which one it should send it to. So hopefully it's very fast, but you're right. Very often it could be that you don't need one, but n because of performance. If you could have a machine that's fast enough to do it, I still would not like to have a single machine, because if it fails, I lose my entire system. So the art of computer engineering is to make reliable systems with non-reliable components. So every computer may crash and will crash one day or hang, so we want to balance it here. If I have only two, how can I make sure now that the rest of the world is not exposed to the fact that I have two? If I go to www.google.ch, I don't have Google 1 and Google 2. I just go to Google. How can that happen? How would you do it? Yes? Using the DNS, so we could manipulate the DNS. We could give two different, to the www.google.ch, for example, we could put two different addresses that correspond to those two here, and that would have the effect. So we can use DNS load balancing. Very often something else is done. DNS load balancing is typically used for splitting traffic across sites. When the traffic has decided to come to one data center rather than another one, very often what is done is equal cost multipath routing. So we will put routers at the head of this, and then there will be the same IP address can be allocated to the two machines. And we have seen that with OSPF, we can have, for a given destination, we can have multipaths, multiple paths of equal cost. In the examples we saw, it was because there are truly several paths that have the same cost to one destination. But for a router that is not at the destination, there's no difference between this and there are two different machines with the same IP address. So you can inject into a routing system, into OSPF, you can inject the same IP address at multiple interfaces. And this will work. Everybody will compute shortest path to one of the addresses, and traffic will go to one of the machines that is the closest from you. If the costs are equal, then by the systems of equal cost multipath that we have in OSPF, you will split the traffic evenly between the two. And we have seen that one of the key things you do when you implement that sort of thing is to make sure that you do per flow load balancing. So different packets of the same TCP connection are very likely to be sent to one of the two machines here. Voilà, we'll do a break now and continue our quick exploration of the application layer in 15 minutes.